In the last two lectures, I've told a pretty impressive story of how the various chemical elements were made inside stars, with a really remarkable match between the predictions of stellar nucleosynthesis and the measured abundances of the elements. It's one of the great success stories of 20th century science. However, I've deliberately omitted one glaring discrepancy: helium. Remember, almost everywhere we look, we find about 25% helium, and that's way more than you'd expect. Even though stars do, of course, make helium, adding up their contribution, we'd expect at most about 1 or 2%. So something is clearly missing from our story. A real clue comes from the fact that the oldest stars still have 25% helium. Here are two spectra. Compared to the top normal star, the lower one has much weaker absorption lines because it has 100 times fewer heavy elements. And that's because it's a very old star, born well before there'd been much heavy element enrichment. And so it's made from almost pure primordial gas. But, and this is the important point, it still has 25% helium. So it seems that most helium must have been made before any stars were born, and that suggests helium was made in the Big Bang. Now, it's perhaps not surprising that the hot Big Bang managed to make at least some chemical elements, and that's going to be the main focus for this lecture, so-called Big Bang nucleosynthesis. So let me start by briefly tracing the history of the idea of a Big Bang, as well as the idea that elements might be made during a Big Bang. In fact, both of these ideas go back to a Belgian cosmologist and Jesuit priest, Abbé Georges Lemaître, who wrote a remarkable paper in 1931. Now, remember in 1931, Hubble had just discovered the galaxy redshift distance relation, and so astronomers began to accept solutions to Einstein's equations that involved expansion. But Lemaître went one step further, and he took seriously the early period of rapid expansion from essentially zero size, and interpreted it as a true beginning, a day without yesterday, to use his wonderful phrase. In fact, Lemaître's motivation for considering this dramatic beginning to the universe was rather unusual. He saw it as a way to make all the elements, but not by building them up, as we now think. He envisioned a huge single atomic nucleus, a few times the size of the solar system, what he called the primeval atom, which exploded and splintered spontaneously, rather like radioactive decay, making all the atomic nuclei and spreading them out where they would later condense into stars and galaxies. Now, perhaps not too surprisingly, this idea wasn't widely accepted, but it was the first time an explosive beginning to the expansion had been suggested. And so Lemaître is now given credit as the originator of the idea of the Big Bang. Now, the next time a Big Bang was carefully studied was in the late 1940s by the Russian émigré George Gamow and his students Ralph Alpher and Robert Herman. They published a number of papers between 1948 and 1953 that used nuclear physics to follow how nuclear reactions within the first few minutes of a rapid hot expansion might construct all the chemical elements. Now, ultimately, for reasons we'll get to in a minute, their theory failed to generate elements beyond helium. But it did make one other very important prediction that I mentioned back in lecture 13. The expanding hot fireball should leave behind an omnidirectional microwave glow, a microwave background, with a temperature of a few degrees Kelvin. They even tried to persuade observers to look for this microwave emission, but no one took up the challenge. Now, in retrospect, it's remarkable that this early work, just like that of Lemaître, never became widely accepted and was essentially forgotten. And it was only in 1964, when the microwave background was discovered accidentally by Penzias and Wilson that most astronomers and cosmologists finally believed in the reality of the Big Bang. So with that brief historical introduction, let's now bring this topic right up to date. Now, ultimately, we are heading back to the 1 minute old universe. So how do we get there? How do we know what the conditions were like at such an early time? It's actually pretty straightforward. Here's the overall situation. As the universe expands, it gradually changes from being hotter and denser to being cooler and less dense. Now, we already have a very good idea of the conditions at 400,000 years because we see that epoch as the microwave background. The universe was 1,000 times smaller, so the scale factor, S, was 1,000th. The temperature was 3,000 degrees. The density was about 250 protons and electrons per cubic centimetre, and there were 1 billion photons for every proton. These are just the conditions I described back in lecture 14. But the important thing to realise is that the physics of expansion is extremely simple, and we can extrapolate backwards in time with confidence. Remember, the Friedmann equation tells us exactly how the universe's size grows with time. So running the clock backwards, at 1 minute, we find the universe was 1 billion times smaller than today. So the scale factor, S, was about 10 to the minus 9. Using this, we quickly find a matter density of about 100 grams per cubic metre and a temperature of about 3 billion degrees. Now, these are extraordinary conditions by human standards, but they're not that unusual cosmically speaking. In fact, you might recognise them as not too different from the conditions at the centres of stars. Now, I've just spent 2 whole lectures telling you that the cores of stars are where thermonuclear furnaces make new elements. So you shouldn't be too surprised to hear that the minute-old universe is ripe for some nuclear fusion. So let's have a closer look at that now. Now, having just said that the minute-old universe resembles the cores of stars, there are nevertheless a few important differences. First of all, the cosmic furnace has a rather different composition. Just protons, electrons, neutrons, and photons in the ratio 7 to 7 to 1 to 1 billion. As we'll see, the presence of free neutrons introduces the possibility of nuclear reactions that can't happen in stars. Now, incidentally, that ratio of 1 neutron for every 7 protons is a key number in this subject, and it turns out that it gets set when the universe was just 1 second old. But I'm going to postpone telling you how that happens until lecture 28, so please just accept for the moment that the neutron to proton ratio was 1 to 7. Now, the other characteristics of the Big Bang furnace are that it has much lower density and it's expanding and cooling very quickly. And both these mean that only fast reactions can occur. Slow ones that normally can occur in stars never have the time to get going in the Big Bang. So what are these reactions? Here's a very simple diagram that shows you the overall process. Before the reactions begin, we have 14 protons in red and 2 neutrons in blue. There's that ratio, 7 to 1. Now, during the reactions, the 2 neutrons combine with 2 protons to make a helium nucleus. So at the end, we have 12 protons remaining and 1 helium nucleus. Now, the overall mass ratio is 12 to 4, or 75% protons, that's hydrogen, and 25% helium. Bingo! There's that 25% helium. It arises directly from the 7 to 1 proton to neutron ratio at the start. Now, in practice, there is a sequence of reactions that occur, and here's the most important first one. It involves combining a single proton and a neutron to make deuterium. Remember, deuterium is a heavy version of hydrogen with an extra neutron. Let's just contrast that with the creation of deuterium in stars. Because there are no free neutrons in stars, the reaction involves the collision of two protons. But remember from last lecture, this reaction occurs via the weak nuclear force and is incredibly unlikely, with the average proton needing 1 billion years to react in the Sun's core. So it's no wonder that this reaction can't happen in the young universe. There simply isn't time. Okay, back to the young universe. As soon as deuterium is produced, it's quickly converted to helium-4 via various reactions. For example, it can get hit by a proton to make helium-3, that's a light version of helium, and this then gets hit by a neutron, and we end up with helium-4. Or, alternatively, it can get hit by a neutron to make hydrogen-3, and that quickly gets hit by a proton, again to make helium-4. Now, in practice, cosmologists enter all these reactions into a pretty sophisticated computer program and solve for the changing conditions and composition. Here's a classic diagram that shows what happens during the first hour. First of all, notice that all the axes are exponential. We have time going from left to right, from 10 to 100 to 1,000 seconds, with a corresponding drop in temperature shown along the top, from 3 to 1 to 0.3 billion degrees. Now, the vertical axis is the fractional composition, from 1 at the top to a very tiny 10 to the minus 10 at the bottom. So you can see that we start over on the left with 6/7 protons and 1/7 neutrons, and that's all. Now, before about a minute, it is too hot for deuterium to form. It's quite a fragile little nucleus, and we need to wait for almost a minute for the temperature to drop to about 1 billion degrees. This delay is called the deuterium bottleneck. Everything is on hold until deuterium nuclei can survive. Now, by about 3 minutes, the reactions are in full swing. Neutrons are being gobbled up by protons, and helium-4 is being generated in large quantities. But by about half an hour, the temperature and density are now too low, and it's all over. The few remaining neutrons decay away, while the other abundances are no longer changing. If we now look at the right-hand side, you can read off the final abundances. 75% protons, that's hydrogen, 25% helium, then way down is deuterium and helium-3, around 10 to the minus 5, and much lower is a trace of lithium-7, around 10 to the minus 10. These are the final Big Bang products from which the first stars and galaxies are made, primarily hydrogen and helium, with a trace of 3 other light elements, and that's it, nothing else. Now, why don't the reactions generate heavier elements? Well, let's have a look at all the relevant nuclei laid out in the kind of diagram we saw last lecture. We have neutron number along the bottom and proton number upwards. And the various reactions move nuclei from one spot to the next. For example, adding a neutron moves the nucleus 1 step to the right, while adding a proton moves it 1 step upwards. Now, I've labelled all the stable nuclei, so notice there are some very important gaps, particularly along the 2 red dashed lines for nuclei with totals of 5 and 8 neutrons plus protons. These gaps block the reactions from advancing up the sequence. For example, we can't add a proton or a neutron to helium-4 nucleus, nor can we combine 2 helium-4 nuclei, since beryllium-8 only survives for a tiny fraction of a second. And this block is called the beryllium barrier, and it's the primary reason why the Big Bang fails to produce any heavy elements. Of course, in stars, the situation is very different. Remember, their helium cores can be incredibly dense, and they hang around for millions of years. And so the triple alpha reaction can jump across the beryllium-8 and get to carbon-12. And once that's happened, the pathway is open and all the other heavy elements can be made. Now let's pause at this moment to reflect on all this. A thermonuclear furnace just burned, in 5 minutes, 100 times more hydrogen than all the stars in all the galaxies that have ever lived. Surely this did something to the universe besides just changing its composition. Actually, the answer is no, not really. First of all, don't fall into the trap of thinking it's like a bomb that would blast the universe apart faster. Remember, we don't have a high-pressure region expanding into a low-pressure region. The furnace fills all of space, so there's nowhere else for it to go. But nor do the fusion reactions heat the universe up much. Remember, there are 1 billion photons for every proton. So when the fusion reactions dump their heat into the gas, it's like you jumping into a swimming pool. Yes, you're warmer than the water, but you don't raise the pool's temperature much because there's so much more water than you. In the universe, there are so many photons to absorb the energy. So in fact, this amazing period of intense thermonuclear fusion goes almost unnoticed, and the expansion continues smoothly, pretty much as if nothing had happened. Now I'd like to return to those final abundances emerging from the nuclear reactions. Here they are: 75% hydrogen, 25% helium, deuterium and helium-3 are around 10 to the minus 5, and lithium-7 is way down at 10 to the minus 10. As you might imagine, those final abundances depend on the conditions in the early universe. It's like baking a cake. How it comes out of the oven depends on the conditions in the oven. So let's now see how those abundances depend on the conditions in the early universe. It turns out that the primary property that affects the reactions is the density of protons and neutrons. This actually isn't too surprising. If there are more particles, they collide more frequently, and that shifts the balance from slower reactions to faster reactions. So what cosmologists do is to run their computer calculations for a whole set of possible universes, all with slightly different furnace density, to see how the final abundances change. Here's a graph of the results. As before, we have fractional abundance up the vertical axis, but now along the horizontal axis we have the proton and neutron density in grams per cubic meter at 3 minutes. Low density furnaces on the left, high density furnaces on the right. So you can see how increasing the furnace density doesn't affect the amount of helium-4 much. That's because it's basically set by the neutron to proton ratio. But changing the furnace density does push the deuterium and helium-3 abundances down quite a bit, while lithium-7's abundance varies in a more complex way. Well, so far I've not mentioned the actual observed abundances of these elements. What do we actually find in nature for them? Are they even close to the predicted values? Now we have to be careful here. These predictions refer to the primordial material, not contaminated in any way by later element formation in stars. But as long as you look at either very old stars or gas way out between the galaxies, you can find this primordial gas and measure its composition. And this is what you get. Immediately you can see we're at least in the right ballpark. Helium-4 is up at 25%, the deuterium and helium-3 are down around 10 to the minus 5, and lithium-7 is indeed around 10 to the minus 10. Now this alone is a fabulous result. We can explain 4 abundances spanning a range of 10 billion by following the hot Big Bang across its first few minutes. And this is already a remarkable achievement, but the situation is even better than this. Why don't we hunt for a perfect match to the observations. Let's extend the observations with their uncertainties across this diagram and look for a furnace density that makes the agreement as good as possible. Here it is, at about 10 grams per cubic metre. The predicted abundances agree almost perfectly with the measured abundances. Because the deuterium line is steepest, it provides the most stringent match. And you can't vary the match much outside that vertical band. So what we've just done is to measure the proton and neutron density in the 3-minute-old universe. It's a little less than 10 grams per cubic metre, with about a 10% uncertainty. Now, this is actually much more important than you might think. You see, because we know the scale factor, S, at 3 minutes, it's about 10 to the minus 9, we can convert the density of atomic matter at 3 minutes directly to the density of atomic matter today. You just allow for the expansion. Of course, that density is tiny, but we can put it into more familiar form by dividing by the universe's critical density, and we get an omega. That's what's given across the top axis. It's omega atomic, and it goes from 0.001 to 1. Now you can see how important this topic is. The abundances of the light elements essentially measure omega atomic, one of the most important cosmological parameters, and we find a value of 0.04 with about 10% uncertainty. This is a fundamental cosmological result. First, it tells us there is nowhere near enough atomic matter to make the universe's geometry Euclidean or flat. Second, with measurements of omega dark matter around 0.23, way more than 0.04, we know dark matter cannot be made of protons or neutrons. It must be some other kind of exotic particle. And finally, now that we know the universe is actually flat, so omega total is 1, we learn that atomic matter makes up just 4% of everything, which is quite a profound scientific as well as psychological result. Now, if you got a bit lost in all of those details, perhaps this will help. Here is a glass of water, and as we all know from high school, it contains H2O molecules, but it also contains a number of D2O and HDO molecules. These are the famous heavy water molecules in which hydrogen atoms are replaced by deuterium, its heavier isotope. So in principle, we could measure the amount of deuterium relative to hydrogen in this glass of water, and from that, figure out the conditions in the furnace of the Big Bang and the abundance of atomic matter in the universe. This is an amazing piece of archaeology. Who would have thought this innocent little glass of water held that kind of secret? But of course, it simply reminds us that we are embedded in the cosmic, and its history is all around us if only we know what to look for. Now, I want to end this lecture by reviewing quite a bit of the last 3 lectures on atomic matter using a rather special diagram. Here it is. It has exponential axes that span a huge range in density and temperature. And essentially everything in the universe falls somewhere on this diagram. So the x-axis is density, from intergalactic emptiness on the left to supernuclear density on the right. And you can see water's density marked along the top. The y-axis is temperature, from almost absolute zero at the bottom to 10 billion degrees at the top. You can see 0 and 100 centigrade close together on the left. Now here are 2 regions of exceptional creativity. The lower region is where complex molecules can be formed. Basically, one needs temperatures sufficiently high for chemical reactions to occur, but sufficiently low not to break weak molecular bonds. And the atoms need to touch, but not be too compressed to break the bonds. Now, the upper region is larger, and it's where atomic nuclei can be constructed. One needs to overcome the repulsion of colliding nuclei, and that starts for hydrogen around 10 million degrees, with heavier nuclei needing around 100 million degrees. But above a few billion degrees, nuclei are shattered and destroyed. So let's see where various objects fall on this diagram, starting with the universe itself. Here's the path taken as the fireball expands and cools. It moves to the lower left, passing through the region where helium nuclei are made in the first few minutes, and ending 14 billion years later in the microwave background. Here are some other objects. Stars occupy this tilted oval with the specific density temperature line for our sun. Clearly, stars have tenuous outer atmospheres, but cores that fall nicely in the region where nuclei can form. These are the high temperature and density furnaces that make fresh atomic nuclei. Now, towards the end of a star's life, two things can happen to these new nuclei. They can get locked away in extremely dense white dwarf stars, neutron stars, or even black holes, or they can get dredged up onto the surface and ejected out into a low-density gas of the interstellar medium, that's ISM. Or in some circumstances, the gas can even leave the galaxy completely and join the hot intracluster medium, ICM. Now, of course, within the interstellar medium of a galaxy, the atoms can gather and cool into denser molecular clouds, DMCs, and from here collapse to make new stars and so rejoin the large oval. This is a wonderfully creative cycle that goes on within galaxies. Gas is continually passing from stars to interstellar medium and back again. And with each cycle, the gas gets more and more enriched in heavy elements. We can even witness this for stars in our own galaxy. Here's a graph showing the percentage of heavy elements in stars up the y-axis against their age along the x-axis. And you can see how the heavy elements have steadily built up over the lifetime of the galaxy. Now, going back to our density temperature diagram, let me now add how the atomic matter is divided among these various different places. About 10% of it is in galaxies, split roughly 9% in stars and 1% in the interstellar gas. Another 10% is in the intracluster medium, hot gas in the vicinity of galaxies. But look, a full 80% of all the atomic matter is still lingering way out there between the galaxies in the intergalactic medium. It was left there by the Big Bang and never managed to fall into any galaxies. Well, if we add these all up, we get 100%, so that's good. But maybe not. Notice we don't yet have any components spanning the region for making complex molecules. Where do we fit into this picture? Well, when stars form, a tiny amount of material goes into the disk that forms planets. Here are planets and their atmospheres. Fortunately, they span the fertile region. And sure enough, here's our biosphere, slap in the middle of it. Now, it's actually difficult to estimate how much atomic matter is in planets and life. But if our solar system is typical, then the numbers are 0.01% in planets and 10 to the minus 20% in biospheres. And that brings me to my final point. In the past 10 years or so, astronomers have found enough planets around other stars to begin to understand what conditions are needed to make planets. Here's a fascinating graph which shows how the fraction of stars with detected planets increases with the star's heavy element enrichment. Clearly, you need heavy elements to form planets. Above 1%, many stars have planets, but below 1%, planets just don't seem to form. And this has an interesting implication. When we point our telescopes to study nearby galaxies, such as this one, there may very well be sentient beings on planets looking back with their own telescopes, studying the Milky Way. But I'm afraid it's unlikely there'd be anyone looking back to us from these extremely distant galaxies in the Hubble Ultra Deep Field. They're too young and haven't yet built up enough heavy elements to form planets and life. I'm afraid the wonderful spectacle of the exuberant billion-year-old universe, like this artist's impression, may have gone unexperienced. The universe wasn't yet ready. Its atom factories had only just got going.